So I want to tell you a story. Do you guys like stories? Yes, everybody loves a story. So I'm not quite James Halliday. I don't draw quite as well as James. But I want to tell you about this crazy, awesome invention I made called the Amazing Doodad. And I invented this thing, and it's so awesome that everybody in the whole world should buy one. So, of course, what did I do? I set up a doodad factory that makes doodads. And in order to power my factory, I need stuff to make it work. And I have this great model. It's kind of, we're in the future, right? So I can do it like cars. I can do sort of an on-demand model where you sort of buy a doodad and then we send you one. Did you guys see the recent South Park episode about Amazon? Where it's just like, I bought this stuff from Amazon and like, I don't even remember what I got. And that's basically my house, where we get a delivery like every day, and then it's like, guess what somebody ordered from Amazon. And nobody actually remembers. And I know that everybody that has Prime knows exactly that feeling. So we're in the future. We can just kind of, you order a doodad, and then we deliver it to you immediately. So it's this kind of on-demand model. And that looks a little bit like this. So everybody's seen a Node server, right, before? Yeah, pretty much? Right, this is the classic Node server, except I added a thing in the middle that said var doodad equals new doodad, and that's about it. So, a basic idea of somebody requests something, and we create the thing that they want, and we get the thing that they want, and we send it. Now, obviously, like this would be fine if my web server could actually deliver everything that my client wanted, right? I want this API request, here you go. This would be great, except for the fact that how likely is it really that my web server can actually have all of the information on it to create a doodad to give to my client? Very unlikely, right? Presumably, your sort of application is a bit more complex than that. There's a bit more kind of interaction going on. So like this kind of request response model is fine up to a point, but really it's unrealistic. So if I really want to make doodads, the thing that I need to do is I actually need a bunch of sort of subsidiary factories. And judging by the latest Apple news, they should be full of 14-year-olds. Right? Whatever. If you buy anything from China, I'm sure it's made by 14-year-olds, sadly. Economics, it sucks. So, I need screens, and I need antennas, and I need knobs and buttons and different things. And I've got all of these kind of subservient factories that are going to deliver that stuff to me. So that's great. Like now I have a situation where I've got all of these kind of factories and they're going to give me stuff. So the obvious analogy is like, these are my web services, right? In order to construct a page, I'm going to pull together a bunch of stuff. This is service-oriented architecture. So here are my different factories, and they're going to give stuff to my doodad factory. So, we've got some trucks. The trucks represent the network, right? So they go from factory to factory, delivering the stuff. And I'm going to get these boxes of parts. So here are my boxes of parts. Now, realistically, I'm not going to get one part at a time. Instead, it's going to be something like, here's a big bunch of parts. Like the factory makes a bunch of parts, and it delivers them all at once. And this is the kind of classic experience that we get when we do stuff. So, I really need a part in order to make one doodad, but what I'm actually going to get is like a bunch of parts. And I'm going to get 3 massive piles of parts for each, representing each factory. And in Node, it was kind of hard to figure out how to represent this. And I finally thought, well, I'm just going to use the file system commands, because it's actually the only place in Node where there is any kind of synchronous I/O is actually file system to help people write command line scripts. This is much easier to write if I pick some other language, but in Node it would look something like this. I get a request, and then I read a file from the 2 different servers, and they bring the parts and they deliver them, and read file sync gives me here's like a massive just like thunk. Here's a delivery of parts, right? Here's all of it in one go. And this is classically how we build stuff. Like I make a request to some web service over here, and then it's like, here's all your information in one go, sir, right? And it really makes sense because in the classic languages, this sense of streaming doesn't exist, so we always do everything by assignment, right? Who writes callbacks in Python or PHP? I don't see any hands, right? like that guy. I guess if you use an event-driven server, so if you use like Tornado or something else, then you're going to get, or Twister, you're going to get callbacks. But in the classic model, we just do these assignments. So like var screen equals go and get my resource. Var dial equals go and get my resource. And if you've ever tried to do like multi-curl in PHP, it's God's own hell. It's awful. So like this is the kind of situation where we're in, where basically we're dumping these massive stacks of data into our processors. And this is threaded programming. So this is basically like when somebody connects to your web server without using an event-driven server, you're basically saying, I need to have enough warehouse space to house all of the data that I'm going to fetch, right? So if you want to go and fetch 1 million rows from a database, you need to have a thread that's big enough to accept 1 million rows, right? And that's actually why if you look at things like the MySQL driver in PHP, they do like pulling. And the reason that they do pulling is because you don't want to have a thread that's big enough to accept 1 million rows. And I've seen this with clients, with my clients, where people build stuff and they'll put the admin interface on the same server as the live production site. And then it turns out that people that are admins can do these great big database queries. So somebody then goes and jacks the thread memory to be really massive so that the admin people don't crash the server. But it means that everybody else is like wasting memory because they get like a massive warehouse to cope with the admin requests while everybody else just needs like a couple of boxes. So how can we improve this kind of factory scenario? So really I only need like one part in order to do this. So I could do something like this. I could use FedEx. And I kind of like this analogy of kind of sticking like something like FedEx in the middle because this actually, I'm going to talk about it in a minute or in a little bit about back pressure, but FedEx is kind of an important concept in this because it's a lot like the network. It's a shared commodity resource. And if you use a network, if you're in a data center, right, there's other people using the network. You don't know what they're doing. You don't know if somebody just wanted to burst like a gig of traffic. You have no idea. So the logistics is always going to be going back and forth. But really what we need is we just need a couple of boxes in order to sort of do our function. So that starts to look something like this, where we've created a server, and then we send off these requests, and we say, what I'm going to do is I'm going to spool up the data. So I'm now going to do this asynchronously. I'm going to go to factory 1 and get screen. I'm going to go to factory 2 and get my dials, and I'm going to spool up the data. So this is where we start to stream. And I don't know if I can get a pointer. Apparently I can't get a pointer. So you can see that I've got a part count, and then actually this code has got a bug in it. Hooray! You can see that I've got a counter for parts, which I forgot to iterate. Silly me. And I've got 2 different callbacks. So I go and get the factory 1, I get the screen. Factory 2, I get the dial. Now we've got these 2 callbacks for data and end. And basically what we're saying is every time factory 1 gives me some data for a screen, I'm going to add that to my screen. So I'm now buffering up like all of my screen data, and then at some point I'm going to call that, right? I'm going to call that and say finish. And finish is going to check to see if I've got all my parts. If it doesn't have all my parts, then it's not going to do anything. If it does have all my parts, then it's going to finish the request as we did in the first example. I actually forgot, you can edit the slide while we're all looking at it. I actually forgot to iterate the part count. So it would be something like this. Sorry? I could iterate inside finish. That is completely true. So this is, this is kind of basically how we're managing this process of we've got these 2 asynchronous things. At some point, we need to synchronize that we have enough information that we can build the doodad and do it. Now, this is kind of okay, right? Like now we're doing it asynchronously. We're not blocking, which is good. This is kind of Node-ish. But we're still not really properly using streaming. Does anybody see the real problem with this? Does anybody have what is the real thing that's not working here, that's making this not streaming? Not you, Dave. Anybody? Right, so I'm buffering everything, I'm concatenating everything. Why am I doing that? What's the problem here? Because I need two parts, but that's okay. I mean, I'm gonna need two parts, whatever. What's the thing that requires the two parts before it runs? Right, doodad. To create this new object, the object creation doesn't stream. The object creation that I'm doing here, in order to make a new doodad, I need two complete parts. So the object creation here isn't streaming. So the limit of the streaming that we can do with this is we're making this slightly more efficient than if it was threaded, right? If it was threaded, we would have to pay all of the cost of all of this memory upfront. And because we don't do that, we can sort of interlock. You can imagine like the curve of memory is going to go up for this, right? So it's going to be like a growing curve. You can imagine the server can interlock a bunch of those together and be slightly more efficient than if we had threads. But because the creation of a doodad widget requires completed parts, this isn't properly streaming. And this is a really important concept because at some point we can do some streaming, but we often encounter bottlenecks. So before I start to talk about that in more depth, I'm going to cover the basics of the Stream API. So the Stream API looks something like this. We've got readable streams and writable streams, and they kind of correspond together. So one side of readable corresponds to the other side of writable. So when we get a data event, the data event corresponds to a write. So a readable stream will say, hey, I have data. And you can see that in the example where did I screw that up as well? No. The response on data gives me data, right? And that then corresponds to a write. So we can take the data event and that pairs with a write. When we get an end event, we have an end call on the writable streams. We also have a pause on readable. We can say like, hey, don't send me any more stuff, and then a resume, which obviously those two go together. Pause, resume, pause, resume. And then we have destroy methods on both. We also have this special method pipe, and we also have destroy soon. The drain event corresponds with pause, but the drain event is kind of deprecated, and I'll talk about that. So the pipe method is kind of clever. You've seen that in this example, I'm using data and end explicitly. Now, because we can see that data pairs with write, and end as an event pairs with end as a function call, the pipe method allows us to join those two things together. So we can easily start to join these streams together and say, this stream goes with this stream, goes with this stream, goes with this stream. And that gives us a bunch of kind of interesting stuff. So streams are really easy to implement. One of the things you'll see is in a lot of the examples I'm using parts of Node, the streams itself is just, it's an API. You can just implement it. So I can include stream, I can create a new stream, which is an event emitter in Node. So notice that this is like Crockwood's class-like syntax, capital S to classes. If I create a new stream, man, I'm doing terribly today. Stream.stream, I suck. You can all boo me at the end. We get our stream, we create a new stream. If we set it to readable, we can now do readable things with it. So we've got these two APIs. By setting the property readable or writable, we define what kind of a stream it is. And then in order to send data, we use the event emitter, so we emit data on the stream. Here's my data, emit my data, emit my data. And then to end it, we just emit an end event. Correspondingly, if we want to create a write stream, we create a new stream, we set writable to true. In this case, I'm adding a data property on top of the stream I created. And then s.write, we have to implement the function. So when we're creating writable streams, we have to implement the functions in the API. So in this case, write, I'm just appending to data. End, I simply log all the data when it's finished. And then for destroy, I say this is no longer a writable stream. And because it's not a writable stream, it's going to stop getting used. And when it stops getting used, it's going to get garbage collected. Right? So all of this is good so far. We've seen like one kind of hiccup where we've got an issue where if we don't have a fully streaming server, we get some benefit but not all the benefit. We also have another issue, and this is a problem with Node. And this is something that we're going to start to address. But if we think of our example, we've got our doodad factory, and it's getting a bunch of deliveries from the parts supplier. And that's because the way that the Node API works currently is we have these data events. And who controls the data events? Well, it turns out that the readable stream controls the data events, because the readable stream is like, hey, I've got data event, data event, data event. So all of these trucks are like our data events, and they sort of, it's basically, we've got this factory, and it's just kind of barfing data at us as and when it feels like. It's like, yeah, we have a contract. I'm just going to send you some parts, like when I have them, that kind of thing. Well, it turns out that like maybe I've run out of, or maybe I have too many parts, right? I've got too many parts, and what do I do now? This is actually like a really common problem, and this is, the idea of kind of if this is all FedEx, right? If this is all FedEx and FedEx are running these trucks, well, that's great. It's like my shared resource. I now have too many parts. So I call the factory and I say, stop sending me parts. It turns out they've already mailed the parts. I don't want any more parts. Like my warehouse is literally full, and some dude from FedEx is going to turn up with like more boxes of stuff. What do I do? And this is a common problem. So actually, when we get under the hood, it turns out that in order to do streams, particularly network streams, there's a whole bunch of places where we have little warehouses. FedEx has a little warehouse, right? The network itself has a little warehouse. There are warehouses in routers along the way, right? All of FedEx's internal infrastructure, right? There are, there's a warehouse in the kernel, right? So like maybe I've got a loading dock, and if the loading dock is full, even if my warehouse is empty, my loading dock is full, right? So there are all these different places along the lines where we have these buffers, and we need some way to be like, hey, buddy, just stop sending me stuff. I'm full. And right now we have this problem where stuff can be in flight and we have no way to cancel it. So this is actually a real problem. To sort of put this into like more of a concrete implementation. So one of the things that people don't, I don't know if I have a slide on that, maybe not. One of the things that people often don't understand about how Node works is the event model is actually run by libuv, right? So on the right-hand side, we've got, this is what Node is. Node is node.cc. If you go and download the Node source code, you're going to get node.cc is like the foundation of everything. It is the C file that loads in all of the stuff, and then it loads in, once all of the stuff is loaded, it then runs the node.js file, which lives in the same source directory, and then at some point it then goes and loads all of that other stuff, right? But node.cc is the sort of root of it all, and it brings in V8, it brings in all the different add-ons, it grabs libuv, and it uses libuv to start an event loop. And libuv is our abstraction between a library called libev, which does event loops, and it has done on Unix for ages, and IOCP, which is Windows, right? So this is our event loop. And there's a bunch of different ways of doing events in Node, and a lot of people don't really understand like what the different things do. So actually, I don't think I have a slide on this, so I'm just gonna grab a terminal and just type instead. Can people see that okay? Yeah? Let's grab VI, because VI is awesome. Snigger. I heard that. All right, so we've got a bunch of different ways of doing events. So for example, if I have something, if you do something like server.on request, what's powering that? Well, what's powering that is event emitter. So the first thing that we have is server.emit. So that's the first kind of thing that we can do. We've also got process.nextTick. And then we've also got set timeout and set interval. Oop. So one of the things I think people often don't understand is how actually all of these things work. This is really important. This is JavaScript. This is one of the most important things possibly to understand while doing node events. If you call emit, it is JavaScript, right? Here is a very simple explanation of how event emitter works, right? If I've got event emitter.on equals function, and then I've got a function that I pass to it, or an event name, and then a function, right? It simply goes e.events, event, I should call that event, event, and then we're gonna push to that the fn, right? And then e.emit equals function. This is like really super simplified, but event data. This is basically how event emitter works, is e.events, event, no, for I equals 0, I is less than that dot length, I plus plus. I write JavaScript like it's 1995, yo. I'm old and I can't learn new things. And then something like that. I don't know. So something approximately like this, where basically whenever you call emit, it basically just goes, I have a list of all of the functions attached to this event. I'm just going to call them one by one. There, here you go. So this is really important, is when you call emit, when emit gets called by anything, it's actually JavaScript. And it basically just calls as much JavaScript until it runs out, and then it's done. Process.nextTick is actually a special queue. It's basically, I'll show the diagram in a second, but process.nextTick is, it's a special big boy queue at the top of the regular event loop, and it's like, I'm super important, and you should call me like next. And it's basically a FIFO queue. And then these guys are kind of interesting, which is basically, if I do set timeout fn 0, and then set timeout fn value, or time, end of the event loop, and that one is end of the event loop after time. So these guys do go into the event loop, but basically, if you say 0, it just throws it on the end. If you say time, it will throw it on the end after at least that time, but not necessarily on that time. So it's not guaranteed. And then set intervals, ditto. I don't actually know if you can call set interval with 0. Probably, I guess you could. I haven't tried that. But this is really important. So if we go back to our diagram, at the top you've got the next tick. But basically, we've got this situation where when we get a TCP connection, what happens is it goes, oh, we've got an event listener on the TCP connection, and then that calls emit, and you basically just bubble a shit ton of JavaScript up. So like the TCP connection goes, oh, I'm attached to a web server. That's like a request, and goes up and up and up and up. So if we go back to, here are our trucks, we end up with this situation where at some point I call stream.pause, and now, holy shit, I have all of these things that are already on my event loop, and I have literally no way to remove them. So we're in this interesting situation with the current Stream API, where because all of that data is pushed from the read stream to the write stream, or whatever's listening, we don't have a good way to deal with that. And this is a real problem. So there's a few things that we can kind of do to that to manage the back pressure. And this is a really important topic, because like managing that defines how efficient our server is. So we can use pause and resume to control the back pressure a bit. We can use that in order to define some things. We can manage the buffer size on our web server. So if you're using Linux or Unix or whatever, you can say like, I want connections to have this much buffer or this much. This is particularly important because if you start using socket streams and like chaining together a bunch of sockets, every single one of them is also going to have its own buffer. So kind of an interesting thing. And you basically, the problem is with the current implementation, you have to write data events that assume that you may get an event after a pause anyway. So you have no way of controlling that. So that just kind of sucks. The sort of concrete things there, when the kernel won't accept any more writes, each socket has an internal buffer. And basically what you can do is when you write's going to give you a false to be like, hey, stop writing at me. But you can also check the buffer size and be like, hey, like I have some like maximum kind of like safe buffer size that I want to, you know, not go over, and I can pause stuff. And then also there's like a few of these things like file system methods. You can see when I create a read stream on the file system, I can actually define from the file system how much of a buffer I want. So I can say to the file system, like, hey, create this read stream from the file system with a certain amount of buffer. That's not the kernel buffer, that's Node's internal buffer. So like some of these are tunables, but there aren't so many of them. So instead we end up with a new API. Isaac, this is still a proposal, but Isaac has readable streams on his GitHub. You can go and look at this. It basically improves a bunch of things. So writable streams are more or less the same. They haven't really changed. But the difference that we end up with is the first one is we can start to configure waterlines. So I can basically say, if you think about my factory analogy, I want like 3 or 5 parts. You know, the minimum that I need in order to start making doodads is I need like 3 parts. But don't send me more than 50, because if you give me more than 50, it's going to be inefficient. So we can basically set a waterline. We can say like high and low marks. We then get a readable event. So basically, instead of a data event, the data event's like blur, data, blur, data. The readable event is like, hey, data is available. Like you've reached your like low watermark to say that you now have enough data to do something sensible. I'm now readable. And I'm not going to take any more than my high watermark. If I get more than my high watermark, I'm going to push back and say, like, don't give me any more data. And then we end up with, instead of having the sort of data callback, where it's actually a callback, instead, we end up with this pulling method. So read length. So this is kind of like some of the other languages. The difference is, the reason why it's still event-driven is this readable event. So this readable event says, hey, now you've hit your watermark, you're safe to read. But I can then go and read length of any length I want. I can pass no length and get all of the data that's available, or I can pass a specific length and get a specific amount of data. And if you've ever written a parser, getting a specific amount of data is incredibly helpful. So this makes a big difference. Now, what we're going to do is when this drops, we can put, and you can use it right now, right? You can go to Readable Stream and use this right now. But we're going to put the old API back on top of this. So we're going to shim it. So if you're used to the old API, you can still use the old crappy broken API. It's not that crappy. It's still pretty good. But you can still use the old API. But if you're doing new stuff, you can do it this way. There is a couple of complications. So if you're using pipe, one of the things that you need to do is you make sure that subscribers must implement a readable stream, because if they don't, then you end up where somebody calls read, and then they get the data. So read is now a direct function call. You read, you get the data back. So if you have pipe and you have another person that's trying to pull read on a particular socket, then you're now going to be in like a weird situation. So that's kind of janky. So yeah, I mean, like basically now the new situation is we start to push out like all of those big like caches back to the web services, and then say, I want you to give me like a truckload of 3. Give me a truckload of 3. Give me a truckload of 3. So we're in a slightly different situation where instead of having to like try and tell the other service to back off at some point when we think we're full, instead now we're in a situation where we basically say like this is my like capacity, and then read. So the next thing I wanted to talk about was types of stream. So the obvious one is simplex. This is something like this. If I, and this is just basically like a readable stream, like a one-directional stream. So if I read a stream, and I get some data, and then I log it out. It's just one directional. Could be a write stream, could be a read stream, but it's very simple. The most common one that people use, and this is kind of like proxying, but it's this idea of a throughput stream. So in this case, this is almost the same example. So in this one, I'm calling console.log. In this one, instead of calling console.log, I use pipe. And process.standardout is now a throughput stream. So it gets data in, and then it immediately ejects it out of the program, right? So we now have a throughput stream. And this is really common where, for example, I might do an HTTP get. So I go off to some like web service and I grab it, and then I bring it back, and then I send it directly to my client. And you can do this with like Nginx or something else if you don't have any other logic. But, even just sticking like a Node server that simply fetches from a remote web service and then delivers it to a mobile client, you'll probably see an efficiency gain if you're using something like Rails, simply because Node won't cost you a penalty to deal with mobile latency, right? So there's a bunch of these kind of implementations where these simple like throughput streams are super, super effective. And there's actually no reason, we saw that we can create streams earlier, there's no reason why we can't write throughput streams that also do interesting things. So when it's doing the throughput, there's no reason why it has to like simply do nothing to the stream. There's no reason why you can't start to modify the stream. And we'll talk about those examples in a sec. And then the final one is like a duplex stream. So this is the idea that you basically connect two things together, and they're just going to talk back and forth. Chatterbot or some other like two-way thing could really implement this. So there's like a whole bunch of stuff here. So a couple of libraries that I want to call out before I talk about applications, and then maybe some questions. Let me check my time. So the first one is JasonStream. So if I had some data like this, and I grabbed this off the wiki, but it's a really good example. So like, here are some database rows. We've got a bunch of rows, and you can imagine it says total rows 129. This has been abridged, but I've got lots and lots and lots of rows. JSON.parse is wicked fast, but it turns out that there's so much data that there's no way that I'm going to get that in a single request, right? So I go and get my requests from my database, whether it's like Couch or Mongo or whatever, and I bring it back. And it's much more efficient for me to be able to do something where I'm streaming it. So JasonStream is basically the idea that by having a JSON parser that can read off the wire, each of these rows atomically could be useful, right? So I may still want to do something atomically on this row in order to build my doodad. So and this is the difference before, was like, in the first example, we had this doodad, and it needed to be a complete thing. It needed to be like, here are my parts, I need to do stuff. In order to create effective streaming services, what you need to do is say, what's the least possible component that I can actually start to act on? And that way, I can start to do things. So I can bring some data in. Imagine, a great way to kind of reduce your footprint is like, if you've got this massive user profile full of information, you bring it back. The only thing you need on this page is the name. So you grab the profile, you get the name, you delete that object. You say, I don't want this anymore. And like, boom, you've just freed up a bunch of memory, right? Now that's very explicit. But in this model, what we're trying to do is we're trying to say, what's the minimum value that I can pull off the wire such that I can then start to act on my data and then forget about it. So JasonStream allows us to do this. The stream parser is definitely, it's not as fast as JSON.parse. JSON.parse is like implemented in V8. The people at Google are offensively smart. And the stuff that they've written natively is awesome. But it turns out that if I'm streaming lots of rows from a database, the blocker is not how fast I can parse. The blocker is how fast can I get stuff over the wire from the database. And we've got a similar thing, not that I recommend this. I did a lot of work with Node.js. XPAT is basically, it's a C library that does XML parsing. There's a couple, Isaac wrote Node Sax, I think. And it's basically XML parsing, streaming XML parsing. It's like stabbing yourself in the eyes with hot knives. I mean, like, think about how awful regular XML parsing is, or like even just like working with a DOM, not super fantastic. Imagine trying to and you know, XML obviously doesn't coerce to JSON properly. Like, imagine trying to pull XML off the wire and then implement it. But it turns out that I can, on my MacBook Air from, I don't know, a year ago, I can saturate an entire core of a processor. Like one core is 100% CPU with 50 megs of RAM, right? So these parsers are so efficient. Like you can use all of your CPU and still only use like 50 megs of RAM. So they're incredibly memory efficient. And depending on what application you're building, if I've got a server and it's got loads of memory, and I'm not only am I not having to wait for the whole object to start acting on my stuff, but I'm also saving all this memory. Well, it turns out that all the rest of that memory can now go to memcache, or it can now go to like some object cache, which means that instead of even like going to my dependent resource, I can now just, fire the thing straight out of cache. So all of this stuff is kind of, it's really dependent on being able to do that. So how do we apply this? Well, I think, there's a few main patterns. The first one is filtering. I have some data, it's coming down off the wire, and I want to take it and I want to modify it in some way before I send it on. This is fairly simple. You still need like a stream-based parser, like a JasonStream or something like that, but it's a fairly simple application. You then, and this is, one of the things that I want to emphasize as well is, we've seen a bunch of different examples. I didn't even touch Socket.io. This API, this concept is completely transport neutral, right? It's completely transport neutral. So you can do this over file system, you can do this over Socket.io and WebSockets, and if you use Socket.io, you get a streaming model, and it turns out that actually under the hood, Socket.io implements it with WebSockets, Flash sockets, long polling, like a bunch of different stuff under the hood. So you don't even see that. So filtering is one huge case. I would say the main thing that's really important is when we're dealing with stuff, one of the common, and I guess I don't have a diagram for this, one of the common things that I see is people build stuff where the actual end result of an application is dependent on a bunch of web services. So I'm going to grab Chrome. Has everybody seen web page test? Has anybody seen that? Nobody seen that? I know, I've been talking to you for a minute. You're like, oh, I forgot that I'm supposed to like respond to stuff. Crap. What's the internet password? What? HTML5 Dev Conf. Okay. That was so, I guess, obvious. I know, right? And because I've got a Mac, it's going to take me about 10 minutes to connect. If this doesn't connect in like the next, oh, there we go. All right. Somebody give me a URL. Anybody? What? New York Times? We're at the front of the queue. Yes. All right. I'm going to keep talking while this runs. So one of the things that I see really often is basically we build these pages that are like SOA. They're like an aggregate of a bunch of stuff. And then we say, my first load time, like my initial load time to the user is dependent on all of these other resources that I depend on. Well, that fucking sucks, right? And primarily it sucks because not only is it dependent on the resources themselves, it's dependent on loading the whole resource, right? I can't flush anything until I load the whole resource. This is, obviously everybody uses Yahoo. I used to work for Yahoo, so I like to make jokes about them. They have Marissa Mayer now, they might actually do okay. But if I do like a Yahoo search for, I don't know, cats or something, notice the search bar just, boom, loads, right? This is a good page experience. And I guess web page test is going to take a long time. The point is that Yahoo flush that top bar before any of the rest of their web services have called, right? And as they start calling, as they start getting results, they can now start to flush content to the page. And this is the ideal situation. Turns out it's quite hard. Building streaming services, not super easy. Here's New York Times. You can see like render, let's see, content download, Wow, they download loads of stuff. So basically, this green line is when it starts to render, and because they start loading within sort of 200 milliseconds, right? That gives them, the difference between 200 milliseconds and when does it start loading? Oh wait, it says at the top, like 2 seconds, right? So it takes them about a second and a half to render the page. Now imagine if their first byte took a second, right? Because they were waiting on all of these dependent resources before they started loading stuff, right? Then you've got a page that takes 3 seconds instead of 2 seconds. And this is the real benefit of streaming servers, is that I can start to say, even though it may take me like this amount of time to do something, I can start to shuffle all these pieces together with the minimum possible delay and get them out the door. All right, thanks. Get out the crap, man.